in our this meeting is being recorded as the Zoom has just reminded us. So it's going to be available later on YouTube. And now that we're at it, I'm going to remind everybody where this YouTube playlist lives. So if you have nothing else to do, you can always go back to some of the previously recorded seminars. It is my pleasure to introduce Professor Arvind Ravikumar. But before I go introduce him, I would like to acknowledge that the most hard work in scheduling this seminar was done by Professor Perch, who is not here, so I'm standing in, and then Leah Freeman, who is around here somewhere, and Tracy McGuire Wilson. So I would like to acknowledge them on putting together this seminar series. So basically now for the rest of the semester at 3 p.m. on Mondays, there will be a seminar. All right, so Professor Arvind Ravikumar is now from UT Austin, but he has gotten his PhD and master's degrees in electrical engineering from Princeton, and has moved to his current position at UT as a research associate professor from Harrisburg University of Science and Technology in Pennsylvania. So this is also a warm welcome to Professor Ravikumar, who is going to establish here a sustainable energy transition laboratory. And his presentation today is essentially going to review the work he's done so far on this topic, as well as what is the future in this area. So without further ado, everybody please do a welcome Professor Ravikumar. Now just a little more of a housekeeping. During the talk, you can just please ask quick questions by unmuting yourself, just as a quick, those that are just like quick questions to explain something, and then let's leave any kind of discussion to more to the end of this talk. And you can either unmute yourself and ask a question or pose a question in chat. And without further ado, I'm going to mute myself and let the speaker take off.
All right, can you all hear me okay and see the slides?
Yes, we can.
All right, great. Thank you so much for that kind introduction, and it's great to be speaking to all of you today. What I'm going to do the next 40 minutes or so is to talk about the energy transition as it relates to the oil and gas industry. And so what we're going to do is we're going to talk about, what do we mean by saying sustainability in the oil and gas industry? The question is why now, and how's this time be different? Some of you in the audience might remember BP's famed Beyond Petroleum campaign about a couple of decades ago, and that didn't pan out very well. But they're again starting a new campaign just last year, and it's good. We think it's going to be different, and we'll talk a little bit about why it's different now compared to what happened before. I'll give a little bit of an introduction to the kinds of skills that are needed to address some of the major sustainability challenges in the oil and gas space. And this is a combination of domain knowledge, understanding petroleum engineering, understanding new technologies that are coming online, as well as systems engineering, the ability to put all of this knowledge and information together and understand how it fits into the broader energy system and energy policy. I'll then go on to talk a little bit about examples of sustainability research that we do in our group. Some of these include methane emissions and policy, carbon monitoring, looking at hydrogen, blue and green hydrogen, and the future of liquefied natural gas. These are examples that directly relate what's happening currently in the outside world, in government, in oil and gas companies, to what we can do and how we can answer some of those pressing scientific questions in those fields. I'll talk a little bit about communicating about sustainability. Just in my experience over the past decade or so working in this field, I've learned a few things about what it means to do research that is sort of policy relevant and salient to the outside world as we speak right now. And so how do we talk to people who are not in academia, and what does that mean for graduate education? And then I'll end with some concluding remarks. So to start with, we are on the cusp of a transformation within the world of fossil fuels, specifically oil and gas. And the pictures that you see on the slide, I didn't have to search much for it. All I had to do was go to the company's website, BP.com, Shell.com, Repsol.com. It's a Spanish oil and gas giant. And all you can see on their webpage are information and advertisements and big images about sustainability, about net zero emissions. And these are just a few examples that I could find in a span of 30 seconds. So BP had this big net zero rollout. Part of the net zero campaign for BP is actually reducing their oil production by 40% by 2030 compared to current levels. They have additional goals as well in reducing their methane emissions, in moving to, in choosing more sustainable fuels, etc. If you look at Shell, they have way more than what I could present here. They have their energy transition strategy. They have their Shell climate target, which is to become a net zero business by 2050. And they're investing heavily into new technologies such as green hydrogen. And the next thing is Repsol. Repsol, like I said, is a Spanish oil and gas giant. They are one of the few companies that have put numbers on their targets of net zero emissions, how their interim targets, and more importantly, the performance of the achievement of these targets are directly related to the compensation for the CEO and top management. So if they don't achieve 50% emissions reductions by 2040, the compensation is much lower for the CEO. So not only announcing targets, but actually putting some meat on it and talking about what will happen if we don't achieve these goals. And it's not just oil and gas companies, right? Players in every major sector are now announcing bold plans for significant emissions reductions. So you have investment companies like Vanguard and BlackRock pledging to hit net zero. You have countries like China talking about net zero emissions or carbon neutrality by 2060. And you have sectors where it's often difficult to decarbonize, where we don't have solutions, talking about reducing carbon emissions and achieving net zero by 2050. Now, let me be clear. A lot of this could be just PR and press statements to get on with the trend about net zero emissions, but it's not just one person or one company doing it, it's everyone doing it. And so there's real momentum behind trying to figure out how do you get to a place that is net zero by 2050. And now if you analyze all of these things, all of these announcements that are coming out of various companies and countries, what we'll see is that oil and gas companies are one of the major sectors that are announcing these targets. And they come in sort of three different flavors. The first one is investments in low carbon businesses, wind, hydrogen, geothermal. You see both US and European majors doing it. Some have announced net zero emissions targets by 2050. The US majors have not jumped on this bandwagon yet, but the European majors are already there, partly because of the policy environment in the European Union. And then even more companies are looking at methane mitigation policies and carbon intensity reduction goals. We have utilities in the US. Several utilities have committed to achieving a 100% zero carbon grid. In fact, many of them are legally binding as they're part of the IRP process, which is the formal way they announce what kind of new electric capacity they're going to build online in the next few years. We have countries announcing net zero and deep decarbonization goals. Some of them are at net zero, some of them are at 80% decarbonization, but major players like China, UK, France have already announced those details. Canada, EU, and South Korea are still figuring out the details of their net zero plans. And the last thing is businesses that are not oil and gas, so energy intensive businesses like LNG exporters, like tech industry, like steel manufacturers are announcing net zero plans, are announcing pilot demonstration projects of low carbon steel and cement production. So it's not just words, there's been a lot of investments going into these net zero targets. Right now, if you look at the United States, this is a map of the electric utility sector, different jurisdictions. And what you can see is a huge transformation that's coming to the sector. Over 50% of US electricity sales currently from utilities have either legally binding or pledged 100% clean electricity standards. And this is going to be a combination of different technologies. Some of them could be just solar and wind. Some of them could be natural gas with carbon capture. Some of them are even thinking of including hydrogen as part of their portfolio. So lot of utilities are thinking about a lot of different technologies, but the ultimate goal is to significantly reduce their emissions footprint. And if you sort of zoom out of the United States, if you look at this issue from the entire world, this is the picture that you get. Global emissions are increasingly coming under net zero pledges. Let's just look at what has happened over the past year during a raging pandemic around this world. In January 2020, there were about 34% of countries with at least a net zero discussion. So emissions of countries that have announced net zero discussions included about 34% of the world. Fast forward to April 21, 57% of global emissions are now in countries that at least have a net zero discussion. And that's huge. And you see the picture on the right, the diversity of the countries and the regions that are talking about net zero or have official targets. India has been recently discussing net zero again because China has done it. But whatever the reason, there are major emitting countries thinking about net zero emissions. And the most important part, and the one that gives me hope about the commitment of these companies, of countries, of investors to address sustainability, is that it's not driven by one actor. It is a convergence of global activism. And when I say activism, I'm not just talking about environmentalists, I'm also talking about investors who want companies to address climate change. It's a combination of global activism, risk aversion, and the growth potential that's available in low carbon businesses. And the future of the oil and gas industry is increasingly depending on the sustainability of energy production. And you see clear difference even among the industry. There are companies that are proactive. They want to explore hydrogen. They want to explore geothermal. They want to see what's coming next in 5, 10, 20 years. And then you see some companies that are reactive, that do not want to change anything on their own unless they are mandated by law to do it. So we do see a diversity in the responses by the industry to this imperative on sustainability, but what we're seeing is a growing chorus of companies and actors trying to reduce carbon emissions over the next 2 to 3 decades. And so what are the different pressures that are on these companies to really move forward on sustainability? The first one is federal policy. The European Union has very strong policies on their climate action and including goals. The United States, the Biden administration has been working on some strong policy. In fact, there are some specific areas like methane emissions where there's bipartisan support, and even lobbying firms like for example, trade groups like the American Petroleum Institute wants federal methane standards. There's investor activism, where people that own majority stake or even some stake in oil and gas companies are requiring them to address the carbon footprint. There's global climate action. There's been a lot of pressure, given that China has also announced net zero targets. There's a lot of pressure in the developed world to also announce ambitious targets for emissions reductions. Of course, then there's new technologies. It's not just driven by external pressure, it's also driven by innovation and development in new technologies. Every day there's announcement of a pilot project or a demonstration project or someone achieving much lower costs than before. New technologies like geothermal, carbon capture and sequestration, green hydrogen are all something that oil and gas companies are interested in and investing in, and that is something that's only going to grow into the future. There's demand side changes. There's been a lot of push. For example, electric vehicles is one example where the costs of batteries and ownership in electric vehicles is going down significantly. And there are estimates by analysts at Bloomberg and even some oil and gas companies that electric vehicle would become one of the largest contributors to reduction in oil consumption for motor vehicles. And it's going to happen very quickly, given the recent growth in electric vehicles and electrification. And the last thing is sustainability targets. Several companies, oil and gas companies, do want to address climate change, do want to reduce their emissions footprint, and so have announced proactively sustainability targets. Some of them are more stringent than the others, some of them are more serious than the others, but the point is all of them are announcing something. So what does this mean for you? So if you're a student in the audience, what does this mean as you embark on your PhD degree? So the goal of our lab, the Sustainable Energy Transition Lab, is to contribute meaningfully to the sustainability conversation and train the next generation of engineers who will lead this transition. there's a famous technology hype curve that you might have seen before that I've sort of superimposed on this timeline from now all the way through 2050. And I'm showing this to you because today's graduate students, and yes, that's you, will be the future leaders of the energy transition just because of the timelines associated with it. So what this line shows is basically what happens when there's significant hype around a certain technology or a certain process. So what you're seeing right now, I think, is we're on the net zero hype phase. Every company, even my local grocer, is announcing net zero emissions targets without really understanding what actually goes into achieving net zero emissions. So there's a lot of hype and interest around that. What we are going to see in the next decade or so, in the 2020s and maybe early 2030s, is a lot of trial and error. You're going to see companies investing in new technologies, investing in new processes, investing in new supply chains to try to address or achieve the net zero goals. There's going to be a lot of disappointment in the process. There's also going to be a lot of successes. And so we're going to figure out by trial and error what's going to work and what's not going to work. And in the 2030s and beyond is when you're going to start to see sustainable solutions. We would have figured out by then, hopefully, which of those technologies and which of those transformations actually work. And we would have to scale up that pretty quickly to achieve our net zero targets by 2050. So beyond 2035 and 2040, what we're going to see is a productive growth in carbon mitigation through all the trial and error and all the scale up that we have done over the past 2 decades. And this is exactly relevant to your own career as engineers with a background in oil and gas. So let's say you finish your PhD by 2025 or 2026. The time you get out into the job market, into the world of sustainability, what you're going to see is that many companies are in the phase of tech pilots. You're going to see carbon capture plants. You're going to see geothermal plants. You're going to see pilot hydrogen projects. You're going to see some electrification projects. The point is that the minute you enter into the job market, you're going to be working on technology pilots, the first of its kind demonstration of new systems that could potentially lead us to a net zero world. And so you will get started on that, developing these technologies, improving them, making them more efficient, making them cheaper, so that 10 years from now, you can start working on scaling up those technologies to the state level, to the national level, and to the global level. A solution that just works in the southeast corner of Austin is not going to be a solution to address climate change. It has to be scalable, it has to be cheap, and it has to be deployable over a wide scale. So that's something that's going to happen once the tech pilots are done. And the last thing is towards 2050 is when we are going to start thinking about net zero realization. Some companies would be getting there already, some companies might have already achieved it, and some companies might be behind. But this is sort of where how technology evolves from today through 2050 sort of parallels your career from getting your PhD and going out in the world looking at careers and sustainability. So the big question is, getting to net zero is not going to mean that the world will stop using fossil fuels, although it is likely to be substantially lower, especially when it comes to natural gas, because the world still has a lot of coal and there's a lot of potential to use natural gas to reduce emissions in the near term. But the real question is this: we are right now here in a world that uses fossil fuels for 80% of its energy needs. By 2050, we know that we have to get to close to net zero emissions or low emissions, say 80% decarbonization. The real question is how? How do we get from a world that's 80% fossil fuels to a world that's net zero emissions? And I think this is the crux of sustainability in the oil and gas world. 80% fossil fuels is 80%, fossil fuels, and much of it is oil and gas. So what does it mean for an oil and gas company, for an oil and gas world to move to net zero transition? And this is where the sort of work that I do comes in. And this is one of those things that is highly interdisciplinary in nature, just because of the different aspects of net zero emissions we're talking about. So there are three fundamental things that are part of addressing this transition, figuring out how to get from 80% fossil fuels to net zero emissions. You have fundamental science, understanding of greenhouse gas emissions from different operations, and what are the energetics of it, what is the ways to reduce them. And then you have new technology and innovation. We have a lot of promising approaches already, many in our own department, things like geothermal, carbon capture, hydrogen are all very important technologies. And then you have systems analysis and policy, which is basically putting all this together and thinking about our energy system as a whole and figuring out, everything is slow here. You buy a house, that house will probably be around for the next 100 years. So thinking about, given the inertia in our energy system, how do these new technologies fit into our energy system? What kind of decisions do we have to make now so that in 20 and 30 years from now, we are on the path towards net zero? So I think of this as sort of an intersection of three different things. You need your domain expertise, which is petroleum engineering. You need to know how oil and gas works in this world. You need to know about new technology and innovation. You need to be able to evaluate them, whether it's hydrogen, CCS, geothermal, and you need to be able to understand how to put them all together and how they fit into the broader energy system. And so, not all the time you find people with all the three different expertise that I show here. So, and this is somewhat of a, I would say, oversimplification, but it rings true in a lot of different contexts. So there are going to be people who only have domain expertise and technology innovation. Yeah, so people who are in the left two circles, domain expertise and technology innovation, they don't understand how things fit into policies, how things fit into the energy system. And I call that the Elon Musk trap. And so his idea of boring tunnels under every major city will solve the emissions problem from transportation might not actually work for a whole host of reasons. And it's not just my personal opinion. There are several detailed studies on how technology diffusion and policies happen in the world. There are going to be people who are experts on technology innovation or on systems policy or domain expertise in system policy. So what I talk about is if you only know your domain expertise and your systems and policy, that intersection is called the degrowth trap. This is people you might have seen talking about, we know oil and burning fossil fuels causes climate change, and therefore we need to stop using fossil fuels, or we need to stop economic growth in the most extreme case of that argument. Those are people who do not believe in technology, who do not think carbon capture or geothermal or hydrogen will actually work. Maybe they're right, maybe they're wrong. But the point is that's a degrowth trap. It's a trap that does not think new technology is going to significantly change our path forward for net zero emissions. And then the last one is what I call the venture capital technology trap. These are people who know a lot about technology and who want to influence policy and systems. And so if you develop an app that says the app will help achieve net zero emissions, I'm sure you'll get $1 billion invested to expand that app. And these are people who do not have the domain expertise to understand that there are fundamental constraints to certain things, to natural gas, to inertia in infrastructure systems that might limit the speed and scale of diffusion of new technology. And so what you really need to really answer questions around sustainability is sort of, you have to be in the middle. You have to be able to have domain expertise, you have to be able to understand new technology, and you have to be able to put that together within the broader energy system. So what I call this, the Goldilocks triangle of sustainability. And so what we do in our group is sort of think about this in this interdisciplinary manner, and we sort of combine different aspects of research to understand and address some of these questions. So for example, we do field work, we do modeling, and we do economic and environmental analysis of oil and gas systems. So, and these are things that are useful for different parts of it, but they're all connected together to answer broader questions around sustainability. So with respect to field work, we look at fundamental science of emissions from oil and gas activity. How do they vary in space and time? Because those questions have still not been answered. We assess new carbon or methane monitoring systems and take part in pilot projects. We then take the data we collect in the field and put them into models. I'll show you an example of how it actually works. But the problem is it'll help evaluate methane mitigation options and understand what happens under the ground, subsurface processes with above ground observations of emissions. We are starting to explore machine learning in developing some of these sustainability solutions. And then we talk about how these things fit within the broader energy system. So for example, in thinking about the role of US liquefied natural gas in global decarbonization efforts, or techno-economic modeling of new systems like hydrogen integration or LNG. So what I'm going to do in the next 10 minutes or so, or maybe 15 minutes, is to give you some examples of how this is done in practice, what kind of research we work on, and how do we address some of the major questions in this field. So I'm going to start with an example of methane emissions. Reducing methane is a big priority for the oil and gas sector, as well as to governments and companies. Why? Because it is a highly potent greenhouse gas. It's also a low-hanging fruit to significant improvement in environmental performance. Most methane mitigation options currently are cost-effective. The important thing is it could differentiate US operations from other regions or companies. One example is this. The US has been trying to sell LNG to European Union and expand it over the coming years. And the sticking point, the sticking point is the European Union currently gets a lot of gas from Russia. Given EU's strict or stringent climate policy, the argument from the United States is that, we have a handle on our methane emissions. Our environmental footprint is much lower, even if you include emissions from shipping the gas from the US to Europe, and therefore the European Union should buy gas from us as it can help achieve their climate goals compared to getting gas from, say, Russia, because their emissions are significantly higher than the US. That is a valid argument, but we don't have a lot of data to prove it. But that is one reason why US LNG companies are actually pushing upstream producers and pushing the federal government to have strong methane regulations in place. And methane emissions is not isolated to one part of the natural gas supply chain. You have emissions all the way from drilling and fracturing through production, processing, transmission, as well as end use. But a majority of the emissions is on the upstream side. The production and the processing is responsible for about 1.6% net natural gas production to be to leak into the atmosphere, while the transmission and end use is about 0.7 to 0.8%. The total leakage is about 2.3%. 2.3% of natural gas that's produced in the United States is emitted directly into the atmosphere. So I'm going to give you examples of how do we study this? How do we understand the science of it? So the first question we want to understand is, how do methane emissions vary over space and time? And for this, I'm going to choose one project that's currently happening in New York State, where New York State has a net zero goal. And the first thing they want to do as part of that goal is to understand what the emissions are from New York State. In many cases, you'll see that states use emissions data from the EPA. They don't collect their own data, even though there's significant variation across states. And so what New York State wanted to do is understand how methane emissions, specifically from the midstream natural gas segment, vary over space and time. So on the left is all the compressor stations in New York. The blue ones are the transmission pipeline stations. The yellow ones are the storage compressor stations. So we decided to fly over every single one of these stations and measure its emissions. And on the right side is a picture of the plane. It's me, my postdoc Hugh, and Mackenzie. She's the scientist who was on the plane while these measurements were occurring. So we flew over the span of about 3 weeks, every single compressor station in New York. The way we do it is something like this. You basically fly around the facility in concentric circles. So you start at a very low altitude, about 200 feet above the ground, and go all the way to 3,000 feet or until you don't see any signature of the methane plume from the facility. And so if you see this graph, the wind is along the white arrows. The blue dots are where you don't measure any methane, or it's basically the same as background methane. You don't measure any methane in the upwind. Downwind of the site, you can see several colored dots, which are enhanced concentrations of methane coming from the facility because there are no other methane sources in the area. And so we do this for all facilities to measure what their methane emissions are. And there are different ways to understand what it is. So we use multi-scale measurements to understand and correlate emissions with operational details. So on the left is sort of a regular iPhone image of the compressor station. You can see 4 stacks. Those are the exhaust stacks of the compressors. And we had an infrared camera on board the plane. So what we did was we were able to measure emissions with instrumentation on board, and we were able to see what part of the station was actually operating at the time of measurement. And so what you're seeing on the right side is the infrared image of the same station, and you can see 3 of the stacks are brightly lit, and they are lit because they're hot. Exhaust from the compressors are very hot, and 1 of them is unlit. So 3 out of the 4 compressors at this facility was actually operating at the time of measurement. And so we can use this information to correlate what's happening on the ground with the emissions that we're measuring. And what we find are that we find highly skewed emissions distribution and strong correlation with operational characteristics. So this is an example. On the left, you're seeing the fraction of total emissions. So from 0% to 100%, and the flux methane emissions from these facilities from 0 to about 250 kilograms per hour. And what you're seeing is that 90% of emissions are coming from sites that have emissions at least 80 kilograms per hour. What this really means is that, the highest emitting 25% of sites, so New York State has about 100 compressor stations. So the top 25 compressor stations by methane emissions contribute to 75% of total methane emissions. So the key to addressing methane emissions in the segment is to finding those highest emitting sites quickly and addressing the issues there. We also found with our collaborators, with the operators, we got some of their operational data as well. So we were able to correlate operational horsepower of the engines of the compressors at these facilities with the flux rate. So we have two distinct regimes. So there's the purple dots and the purple line, and then there's the blue dots and the blue line. So the purple dots here are sites that had natural gas engines as the prime mover. And so you can see a much stronger correlation of methane emissions with the engine power. On the other hand, facilities that use turbines also had methane emissions, but you can see that the slope is much lower, which means the methane emissions from that site is not necessarily because of operational horsepower, but because of fugitive emissions or leaks in the facility that could potentially be fixed. And we can also see that sites that have turbines have significantly higher operational horsepower and capacity than sites that still use engines. And so how are these data being used? So midstream operators are now working with us to sort of identify sources of these methane emissions and thinking about installing new technology to address them over the coming months. In the meantime, the New York State is now updating their methane emissions inventory as we speak. Part of understanding, what this means and reducing the cost of emissions reductions is assessing new technologies that helps you find these methane emissions. I just said, the highest emitting 25% of the sites in this case was responsible for 75% of total emissions. So the question is, can we quickly identify those 25% of sites? And so what we also do in the group is sort of evaluate new technologies to detect methane emissions. If you looked at any press release or even search on Google on methane emissions, one of the most important things you'll see is the proliferation of new technologies, drones, planes, and satellites. And the question is, how do you know these technologies work? The brochure that the company gives you might be data from lab tests. And lab tests, as we know, does not correlate very well with what happens in the field when you take them out to a producing oil and gas field. And so the goal is to consistently and fairly compare new methane leak detection technologies so that we can provide an independent assessment of performance to operators and regulators. And so we have several field campaigns to test these technologies. We just finished the Mobile Monitoring Challenge a couple of years ago, the Alberta Methane Field Challenge, and concluded right before the pandemic started in Alberta. But all of this are basically taking these technologies. So in this picture, you see a drone and you see a sensor that's mounted on a truck. And you're seeing more pictures here where we measured emissions from producing oil and gas sites around in the US and Canada. And what it does is it tells us data on things like detection probability. Can this technology detect a methane leak? It tells us about quantification accuracy. How accurately can it tell me what the flux rate of methane is? It can tell you about false positivity rates. And this is really important. If a technology keeps telling you there's a methane leak and then the operator sends someone out to the field and then finds no methane leak, that's additional cost, which is not reducing any emissions. So false positivity rate is an important parameter. And control testing helps us sort of estimate fundamental technology performance parameters to be used in modeling. So what we do here is something like this at the end of the day. So you have 4 technologies in this example: handheld, drone, plane, and satellites. And then you have a set of characteristics. Do they detect methane? Do they quantify methane? Do they need follow-up repair? For example, if a plane tells you that your site number 42 is leaking a lot of methane, it doesn't exactly tell you what on site 42 is leaking. It just tells you there's a problem in site 42, which means you need to send someone to that site to find out what exactly is wrong. So some technologies, often drones and planes, will require follow-up action. And the last thing is inventory development. Are the emissions estimates accurate enough that you can actually use it to update your emissions inventories? Some technologies have good accuracy, some don't, and there's a wide range. And the point of this is these technology studies are used for choosing the right technologies for deployment. Regulators use it to evaluate technologies for approval in LDAR programs. LDAR stands for leak detection and repair, which is a standard methane policy where operators are required to go out and look for leaks and then find the leaks and fix the leaks that they find. And for scientists, they provide valuable field data as input to emissions and policy models. So why do you need a model? So the model is needed because technology effectiveness is not the same as mitigation effectiveness. To evaluate how effectively you can reduce your emissions, you need models. So there's two different questions here. The first question is, can a new technology X on platform Y, in this case a drone, detect methane emissions? Yes, we can test it and find out. But the question for policy and for operators is slightly different. So the question is, and can an LDAR program, leak detection repair program with technology X, platform Y, surveying the site, say 12 times a year in basin B, under these weather conditions and repair rules, reduce emissions by 50%? The right-hand question is a very different question than the left-hand question. And to be able to answer the right-hand question, we're going to need models. And one of the models that we developed in our group is FEAST. FEAST stands for Fugitive Emissions Abatement Simulation Tool. It's a Markov chain model that provides a consistent platform to compare technologies and help operators make robust decisions on methane mitigation. So what does it do? It takes in data from all the field trials that we talked about, from all the technology assessments that we do, and takes in policy parameters. And so it puts this all together and answers the question that we just asked. Can this technology, surveying 12 times a year at your facility in the Permian Basin, help reduce emissions by 50% after 3 years? And that's what this model does. It tells you, it talks about technology equivalence. What is technology equivalence? It is basically asking, if I want to replace a drone-based program with a plane-based program, what else do I have to change so that my emissions reductions in the end remains the same? So let's say your target is 50% emissions reductions. Then the question is, what should I do if I'm using a drone versus what should I do if I'm using a plane? And that's one of the most, that's one of the current uses of this model. The EPA and several states are thinking about introducing some of these new technologies. And the first question is, what should I do if I'm replacing what I'm using currently, which is a handheld camera and walking surveys with, say, a drone or a plane? And that is something we do. So in this example, in this figure, what I'm showing is emissions reductions from 0 to 100% as a function of the number of surveys you conduct every year with different technologies. So you can do as low as 1 survey per year, all the way to 12 surveys a year. And so there are two curves here, the orange and the purple. The orange is the current standard, which is the optical gas imaging or OGI survey. And the plane is the new technology that's been developed. And so there are two dotted lines at 40 and 60. Let's look at the one at 40. So what this is saying is, to achieve a target of 40% reduction, you can either survey once a year with the OGI technology, or you can survey 3 times a year with a plane technology. And so if an operator, if a company says, hey, I want to use a plane because it's cheaper, what they'll have to do is, okay, if I'm using a plane, then I'll have to survey 3 times a year to achieve the same 40% emissions reductions. And this varies by basin, it varies by weather conditions, and it varies by technology. And this is something that we do. And more recently, we have been asking questions like, can we use machine learning, for example, to improve sustainability of oil and gas operations and help reduce the cost of mitigation? The challenge, I think, as I said before, is that it is a time-consuming process. Methane emissions are addressed using leak detection repair surveys at each site, which means you literally have to go to each site, find out what's emitting, and fix them. And because we know that most emissions are concentrated on a very small number of facilities, by the time you get to those facilities, you might have spent a month in the field trying to look for methane leaks. So it is time-consuming and therefore expensive. And so what we did was, this was a very preliminary exploratory type of project. We tried to use machine learning to see, instead of let's say you have 100 sites under your control, and you have to survey every single one of them. I mean, the way currently it's being done is you just randomly visit every single site until everything is complete. That's the gray line on the figure. So it's just a random order for your survey. And so you achieve 50% emissions reductions by day 12. But what we did was we developed this algorithm and asked the question, can machine learning predict the order for the survey? The question was, can the machine learning tell me the probability that a site with these characteristics is likely to be a super emitter site? And so we asked the machine learning algorithm to give us a probability. We ordered the sites in order of highest to lowest probability and visited the sites in that order. And as you can see, the red line here shows that we achieved 50% emissions reductions by day 7. That's a 50% reduction in time, which will translate to a 50% reduction in cost. And that is a huge deal in terms of reducing the cost of methane mitigation, where numbers are often looked at in terms of 10% improvement, 20% improvement. This is a 50% improvement, and there's a lot more where this came from, because we are just starting to peel back the power and the potential for machine learning to address these issues. So now I'm going to take a break and sort of go back to the broader system level analysis, figuring out where all of this fits into our transition path. So one example here is analyzing the path dependency in emissions intensity of blue and green hydrogen. So what we did was we built, this is an international team of collaborators from the US, Canada, and the European Union. We built a life cycle model of blue hydrogen and identifying pathways for decarbonization. And one of the things we did is, we talked about, what kind of limits do you need to put on your methane leakage and your carbon capture rate for blue hydrogen to be more emissions, to be less emissions intensive compared to existing electrolysis. And the question is, if blue hydrogen is something that we want to look into, which US basin is best suited to supply gas for blue hydrogen? So for example, let's say you want to reduce your emissions to 50 grams per megajoule. What that means is your methane leakage has to be between 2 to 3%. Clearly, the Permian Basin from recent studies have shown that it is significantly larger than 3%. So if you're going to use blue hydrogen as a means to reduce carbon emissions, then clearly you cannot be using gas from the Permian Basin, because its methane emissions intensity is so high that it's going to negate any benefits from blue hydrogen production. So thinking about questions like, if the United States, for example, is going to go big into blue hydrogen, where would it be most suitable to put blue hydrogen to give us both economic as well as emissions benefits? And it's not just limited to blue hydrogen. Every piece of our infrastructure, whether it's blue hydrogen or geothermal or carbon capture or LNG, once you build it today, it's going to be around in 2050. 30 years is sort of the minimum lifetime of LNG. And so what we looked at is, it's not 30 years, it's not a lot of time. There are decisions being made today, investment decisions, that will decide the future of global carbon emissions. And so what we did was, we started thinking about what does this mean for US LNG, and in fact, global LNG expansion. As you know, LNG is sort of in a renaissance mode. There's been significant global growth in US, Canada, Qatar, and Australia. And what does this mean for our climate targets? So one of the things that we saw is that we looked at every possible new LNG export and import terminal around the world. What we find is that 50% of global LNG capacity is yet to be operational. They are in various stages of development. Some of them have started construction, some of them have been approved, but they're all yet to be operational. And so if the goal, if you look at every one of these proposals, is to use LNG to reduce carbon emissions through coal to gas substitution in the power sector, just like it has happened in the United States. And what you're looking at, this violin plot of export and import LNG terminals around the world, what you're seeing is that 80% of LNG capacity is less than 10 years old. This is important because by 2050, all of this is going to be around. And so how can we make best use of these facilities so that we achieve our carbon reduction goals? And the problem is, every LNG terminal wants to say that they're going to reduce global carbon emissions using coal to gas substitution in the power sector. But the problem is, if you look at where the coal plants are and where the gas pipelines are, you see a discrepancy. The places that need to get away from coal the most, places like India and China, are also the places most likely to not have gas pipelines. So you can build all your terminals, but if there's no way to get the gas from the coast into wherever your power plant is situated, that's going to be a problem, because then now you need to build power pipelines. And that's a significant investment as well as time and effort. And so what we did was, this was a geospatial analysis that one of my postdocs did, looking at all the pipelines, gas pipelines in the world and the coal plants, and calculating the nearest distance to a gas pipeline for each coal plant around the world. And what you're seeing is this distribution. So there are coal plants that are almost sitting on top of a gas pipeline, so very close to it, as you can see in this graph, that has 10 to the minus 1, or like 100 meters or less than a kilometer. But there are also coal plants that are very far away from any gas pipeline. For example, some coal plants in India and China are hundreds of kilometers away from a gas pipeline. So if you look at the coal to gas transition in the United States, the average distance between the coal plant that got converted to a gas plant and the nearest gas pipeline was 28 kilometers. And if we use that as some sort of benchmark, what you're seeing is that 40% of global coal capacity do not have access to gas pipelines. And most of them are located in India and China. So this is a problem if our goal is to use LNG to reduce carbon emissions through coal to gas switching, because the places that have most coal do not also have the pipelines to take the gas from the LNG terminal to the coal plant. And so this is something we want to work on. And there's a lot more to be done here, because as I said, a lot of these plants are going to be around for the next 20, 30 years. And so what I've done over the past 20 minutes is give you a glimpse of the different kinds of things that we do in the lab, understanding and addressing some of the major sustainability challenges in the United States and the world, specifically with respect to the oil and gas industry. And part of this work, given that LNG, methane emissions, pipelines are all sort of very much in the news these days, communication becomes an essential part of the research that we do in the lab. And what I think, and this is now my personal opinion, is that external engagement and communication is an integral part of sustainability research, and really being a scientist in the 21st century on topics that are relevant to the public discourse. So the way I see it is this: the impact of your research, the impact of your paper, or the impact of your work that you do in grad school starts when you publish a paper. Everything you do before that, nobody knows, or a very small group of people will know. But public engagement starts when you publish something, when you publish a paper. And that's when your scientists, your collaborators, and maybe some NGOs will start looking at it. The next stage is conference and seminars. You go to the AGU conference, you go to SPE conferences where other scientists will look at it. There will be some industry attendants at these conferences who will also learn about your research. And then you have social media. Different social media have very different strategies for engagement. So you have Twitter, you have TikTok, you have Instagram, but that's exactly where you start getting your research out to a slightly broader audience. You have journalists, you have the industry, you have the general public who are actually watching social media and looking at what new research is coming online. And I can give you examples if you come and talk to me later on exactly how social media is helpful for your research. And then you have traditional media, radio, TV, print, and now there's Substack. This is where you start engaging policymakers. You start engaging management at oil and gas companies to really transition from your research solutions to a scalable solution for sustainability. And then the last thing is talking about public hearings and policymakers. And as you see, and I can give you actual examples of things happening, is you'll get increased citations, invitations, and funding by engaging in these different non-traditional forms of engagement. And communication is a skill to be learned, just like riding a bike or writing a paper. It is something that doesn't come to you. It's not something that you're born with. It is something that you learn. And there are different strategies that we can implement, and we can learn how to communicate our research to the outside world. All right, concluding remarks. So sustainability will be the defining theme of the next 30 years. Major companies, governments, investors will need experts to fill growing needs in science, engineering, and public policy. At the same time, the details of the transition from an 80% fossil fuel world to a net zero system is unclear. And you need advances in engineering, where we have a lot of different technologies, as well as policy, thinking about what is the path dependency of new technologies, what is the path dependency of their diffusion, what is the cost effectiveness of some of these new systems. And making an impact in this field requires the ability to sort of articulate and work at the intersection of multiple disciplines. You're going to have strong domain expertise just being this department. You have to understand how new technologies work, and importantly, how that fits into the broader socio-economic energy systems that we have in the world. So you want your PGE background, plus an interdisciplinary toolkit that will help you develop effective sustainability solutions. So what we want to do is analyze the state of the science, explore how new technology fits into sustainability goals, and more importantly, analyze sort of future pathways and policies for decarbonization. And all of this has to be done with the idea that communication is going to be an essential component of a 20th century graduate education. But with that, I am going to thank all my sponsors and see if there are questions.
Thank you very much. Excellent talk. So questions, I think we have a group that should be small enough that you can just unmute yourself and ask a question. Or if you type it in chat, I can read it out. Anyone wants to?
Should I start answering questions from the chat?
Sure.
All right. Hey, Sylvia. So Sylvia is asking two questions. So do you know how they come with net zero by 2050? Why 2050? So that's a great question. So then, I mean, targets, especially specific time targets, are more of an art than science. But where it comes from is the IPCC process. When IPCC puts out its report every year, they have some targets. There is what you call a summary for policymakers. The report itself is thousands of pages. The summary for policymakers is probably 15 pages. That is something that every government has to agree before it can become publicly released. And so a lot of these targets, net zero by 2050, comes from the IPCC reports, where research suggests us to be on the Paris Agreement goals of limiting peak warming by 1.5 degrees Celsius by the end of the century. You have to be somewhere near net zero emissions by around 2050. It could be 2055, it could be 2060, but around that time frame. And so that has become sort of a standard benchmark for everyone to use and have a target on in thinking about their sustainability future. All right, do you monitor the public announcements and investments from ONG companies in wind, solar, geothermal, hydrogen, and CCS? This is a great question. I don't personally monitor all of them. I do look at investments in hydrogen and CCS, especially when it comes to the stage of pilot projects. But there are a lot of NGOs in the United States who are actively looking at this. In fact, some of my figures are from their own database, looking at pilot projects that have been announced. The Global CCS Institute is a great resource, especially for CCS projects around the world.
There's one more. Is there a pipe network for hydrogen for gas stations? Is it too late for hydrogens?
Versus you? Oh, that is a great question. So I don't work too much on transportation policy, but from what I understand, speaking with experts, is that hydrogen is seen as a resource for seasonal storage when you have energy demand that varies by season. And it's also seen as not a substitute, but to decarbonize the commercial and residential sector with hydrogen diffusion in an existing pipeline network. As I understand, at least in California, where they're trying to actively think about hydrogen networks, it's a much more logistical challenge because electric vehicles are significantly farther ahead along the curve of innovation and deployment compared to hydrogen-based solutions for transportation. But heavy transportation trucks is still an open question. Whether batteries are the best solution or we need CNG or hydrogen is something that's still an open question.
Are there any other questions? It seemed that some of them went directly to you because I didn't see them in the chat.
Oh.
I'm glad you did. All right, there's one more. do you think gray hydrogen will still be economically feasible if fracking is prohibited in the United States?
That's a good question. I mean, the short answer is I don't know. And part of the reason is I don't know what fracking is prohibited means. I think this is something a lot of environmental NGOs who wants to keep fossil fuels in the ground have thought about. And I think there are none or very few legal options to actually prohibit fracking across the country. So I don't know if that's possible, but if it is, then the economics of gray hydrogen using natural gas imports is something that needs to be worked out. But I think there are so many things we could do before we even start thinking about prohibition of fracking, given the world that we're currently in.
And can you comment on green versus blue hydrogen? Maybe define them quickly.
Yes, so blue hydrogen is you take natural gas, convert it to hydrogen, and then use a carbon capture plant to remove CO2 emissions. Green hydrogen is not using natural gas, it's using solar or wind or geothermal or any zero carbon power to do electrolysis of water and create hydrogen. So there's no CO2 emissions involved. So carbon capture, yes, then that is blue hydrogen. No carbon capture, all zero emissions technologies, that is green hydrogen. So green versus blue is a very hot topic. In fact, we recently submitted a paper, the one slide I showed to Energy and Environmental Science. It's in response to a different paper by a couple of scientists I won't name here, who published basically saying that blue hydrogen is not going to work. Its emissions is worse than just steam methane reforming. And we did find out that their analysis was not complete. They had left out some of the advanced technologies that are coming online for blue hydrogen, and so we had we assembled a team together from around the world to write a paper specifically saying, there are new technological advances. Yes, blue hydrogen might be as bad as steam methane reforming, but it really depends on two factors. The first one is methane leakage from where you get your natural gas. And the second one is capture rate from a carbon capture plant. So yes, blue hydrogen can be substantially lower emissions, but if you satisfy these two conditions.
Any other questions? We're close to 4 o'clock and a lot of people might have. There's one more. Will you be working on projects related to CCS or geothermal in the Sustainable Energy Development Lab or in your lab?
Good question. CCS, yes. Geothermal, maybe, but these are all, I'm always open to collaboration. So if that's something that folks are interested in, very happy to see where we can work together.
Are there any more questions? Here. As we're closing in at 4 o'clock, we're losing audiences. People have other. They have to jump
I'll
on
ask.
another Zoom. There's more.
I'll ask the question.
All right, go ahead,
Masha. So, and I'm sorry if you already addressed this. I don't think you did, but there's choosing the winning technology approaches to this, and there's outcome-based approaches to this, like a certain level of carbon emissions, which some people say a carbon tax would address that. But so governments kind of choose both sorts of things. But we have municipalities banning natural gas in new homes, and we have government subsidies of certain kinds of renewable energy and stuff like that. Where do you see all of those things being useful, or do you think there's a better way to do things?
That's a very good question. It's also a challenging question. My own personal view of this is that you need to target the right policies for the right technologies. For example, there is a place for something like a carbon tax to work, but carbon taxes will not work in every scenario. For example, in the power sector, the price differential between coal and natural gas and renewables are very small, that if you have some carbon tax, a reasonable carbon tax, like $30, $40, $50 per ton CO2e, that will significantly change the type of technology that comes online, the type of electricity that gets sold first in priority order. You've seen this at work in the United Kingdom. You've seen this at work to some extent in Canada. Now, will a carbon tax of $50 per ton work in transportation? Will it make people suddenly stop driving internal combustion engine cars and move to electric vehicles? No, because the $50 per ton CO2 is 50 cents on the gallon. And just normal variability in oil prices would show up as 50 cents in the gallon. So that will not significantly change behavior. So if you want to incentivize electric vehicle adoption, then you need to directly subsidize it. Same for things like hydrogen or geothermal, because these are all very early stage. They are not at the place where a small carbon tax is what prevents them from being adopted. There are deep technological and deployment challenges that needs to be solved, where direct subsidies are a much better and faster way, dare I say, to ensure that technology works, rather than just putting your hopes on a carbon tax and hope that it'll work 30 years from now.
Thank you.
Are there any questions? If not, many thanks for giving an exciting talk. As a reminder to everyone, these talks are recorded and they're on UTPGE YouTube, or will show up on the YouTube for UTPGE. And we see you in the next installment of the talks next week. Thank you.
Thank you.
Thanks, Arvind.
And John, thanks for asking a question in person. You're the only person who dared ask.
Sorry, I was worried. I was watching the talk and then I was going back and forth because my dog was getting sick next to me.
Uh-oh.
Arvind, great talk. I sent you another comment, so let's connect in the following days to talk a little more.
Yeah.
All right, excellent.
Thank you.
Thanks. Bye-bye.
Bye. All right. I think we can close the talk.